Here's the goal. Given the root of a binary tree, list its boundary in anti-clockwise order. Start at the root, follow the outer edge, and include each node only once. Think of it as tracing the tree's outline without stepping inside. Left boundary means the nodes you meet when you go down the left edge of the tree. We collect them from top to bottom. But we skip leaf nodes here. It's just the outer left spine, not the leaves at the bottom. Next, we gather all the leaf nodes. These are the nodes with no children. We scan the whole tree from left to right and list every leaf we find. This step ignores whether they're on the left or right edge. If it's a leaf, include it. Right boundary means the nodes along the tree's right edge, again excluding leaf nodes. We want them in bottom-up order, so we collect the path and later add it reversed. Think of reading the right spine from the bottom back to the top. Here's the output order. Start with the root if it isn't a leaf, then the left boundary, then all leaves from left to right, and finally, the right boundary in reverse to make it bottom up. This sequence walks the tree anti-clockwise without repeating nodes. For example 1, we trace the left boundary. Start at the root, 1, then move down to 2. We stop before 4 because it's a leaf. So the left boundary, excluding leaves, is 1 and 2. That's our left edge for this tree. Now gather the leaves in left to right order. In this tree, the leaf nodes are 4, then 8 and 9 under node 5, then 6 and 7 on the right side. We read them across the bottom as 4, 8, 9, 6, 7. For the right boundary in example 1, walk down the right side and ignore leaves. Starting at 3, the next node is 7, which is a leaf, so we skip it. That means the right boundary, excluding leaves, and written bottom up, contributes just 3. Now combine the parts for example 1 in anti-clockwise order. Left boundary, 1, 2, then leaves, 4, 8, 9, 6, 7. Finally, the right boundary bottom up, 3. The final boundary traversal is 1, 2, 4, 8, 9, 6, 7, 3. In example 2, trace the left boundary from the root. We start at 1, move down to 4, and stop there because the next node, 3, is a leaf. Excluding leaves, the left boundary is simply 1 and 4 for this smaller tree. Now combine example 2. Take the left boundary 1, 4. Add leaves from left to right. 3, then 2 on the right. There are no extra right boundary non-leaf nodes to add. The final anti-clockwise boundary traversal is 1, 4 at 3, 2. We will build the tree boundary with 3 simple passes. First, walk the left edge from the top, skipping leaves. Then, collect every leaf from left to right. Finally, walk the right edge and add those nodes in reverse. Together, these passes match the boundary definition. For the left boundary, start from root's left child, move downward, always taking the left child if it exists. Otherwise, take the right child. Add each node you visit, but do not add leaves. This builds the left edge in top-down order. Now collect leaf nodes. A leaf has no left child and no right child. Use a recursive traversal, visiting left subtree first, then the node, then the right subtree. Whenever you see a leaf, add it. This naturally gathers all leaves from left to right. For the right boundary, start from root's right child. Move downward, taking the right child when possible. Otherwise, take the left child. Add only non-leaf nodes to a temporary list. At the end, append them in reverse to get bottom-up order along the right edge. Put it all together with these steps. If the root is not a leaf, add it first. Next, gather the left boundary. Then collect all leaves from left to right. Finally, gather the right boundary and add it reversed. That sequence builds the full boundary list. This approach runs in linear time O of n because each node is visited once across the 3 passes. It uses O of h extra space for recursion, where h is the tree's height, since the call stack grows only along the longest path. Here's the plan. We drop recursion. We gather the left and right boundaries with simple loops. For leaves, we use Morris Traversal, which makes temporary links so we can visit nodes without a stack. This keeps time linear and space about the tree height. Left boundary is easy with a loop. Start at root left child. While the node exists and is not a leaf, record it. Prefer moving to the left child. If missing, go right. This walks down the outer left edge without recursion, capturing only boundary nodes. Morris threading lets us traverse without a stack. For a node, find its in-order predecessor. If that predecessor has no right link, point it to the current node and go left. When the link points back, remove it and move right. These temporary links vanish when done. To collect leaves, run Morris Traversal and only add nodes that have no left and no right children. If a node has no left, check whether it is a leaf, record it, then go right. Otherwise, create or remove the thread and continue, avoiding any recursion or stack. Now the right boundary. Start at root right child. While the node exists and is not a leaf, push it to a temporary list, preferring the right child, otherwise the left. After the loop, append that list in reverse, so the order runs bottom up along the right edge.